can do something better. And it turned out we did better, and it turned out that we could even now explain the physics of earthquake with the help of artificial intelligence or machine learning things. All right, so I'm going to start with one simple simulation of earthquake, like how earthquake propagate, like how earthquake break through a fault. And this is a southern California earthquake region, and you see here San Diego here, Los Angeles somewhere here, and this is the San Andreas fault. So from here you might think that San Andreas fault is pretty linear, like almost linear, right? But if you look and zoom in, then it's going to be very complicated, and there are lots of variation, local variation there. All right, so this is the epicenter here. So we're gonna simulate an earthquake that have a magnitude of 7.8 magnitude. So this earthquake starts from here and is gonna break all the way from here to up to here. So it's gonna break. So I'm gonna start with this simulation and see how it goes. Simulation started. And you see earthquake kind of like started there, and it's going to rupture the whole fault from here. And as you see here, there are two types of wave. So you see green here, or bluish kind of thing, and the red. The red is the tip of the earthquake that has been breaking. Okay, and the blue is like whenever any earthquake happens, there are several types of waves generated. So one of the fastest wave is called the P wave, or the primary wave, that propagates very faster. This is what you see. P wave is kind of traveling very faster, and the red part or the yellow part is called S wave, or the shear wave. That's what we feel. Like whenever we feel any kind of shaking, so we feel this S wave. Not this P wave. This P wave is very faster, but it's not destructive at all. Okay, so that's what we see. And you see here, this earthquake is able to break the whole fault from that epicenter up to, from epicenter to here. And let's see it's gonna propagate. And you'll also see some of the earthquake will feel lots of shaking around this Los Angeles basin. You see here lots of wave, red wave kind of propagating around this Los Angeles basin. It's because Los Angeles has lots of soft sediment, and they have very less hard rock. That's why if any big earthquake happens right there, the Los Angeles would be very impacted at this time, because of the sediment and the nature of the rock they have deposition there. All right, so you now get the idea like how earthquake propagates from one place to another, and how wave propagates from one place to another. So, all right, so then what is the problem? So we can simulate earthquake, we have the data, then what is the problem? The problem is still we cannot predict earthquake. Still we cannot predict the rupture of earthquake, whether if this, that's the simulation, right? We can do all sorts of analysis with the simulation, but the reality is totally different. We cannot predict earthquake. Why? Because we don't have data. Why we don't have data? For example, say this is a slice of earth, for example, and this earth is pretty big, and this we can go down to deeper earth, thousands of kilometers, hundreds of thousands of kilometers, and we cannot dig the earth to get the information. So we do not know what's going on underneath the surface, right? That's why we do not have enough information. And not only that, faults are very complex. Very, very complex. Say, and in the last slide, you saw that this fault is like almost 1,000 kilometers. So we cannot monitor this 1,000 kilometer fault meter by meter in this low resolution, right? We can from the satellite image, but this satellite image wouldn't be able to provide you lots of data, like what is the stress condition, what is the material properties, and all sorts of analysis. So you don't have data. We don't have data. So that's the problem. That's why, since we don't have data, and since we don't have this technology or resources, we rely on some of the other indirect method. For example, like seismometer. So using the seismometer, we capture the wave. But this seismometer are placed, like, for example, one seismometer placed here in Nashville, other seismometer placed in Cookeville. But in between Nashville and Cookeville, we are losing lots of data. We don't have enough data. But we have only point in these two places, wherever the seismometers are. But we are losing data in between these two places, okay? And we also use indirect method like gravity, magnetism, satellite images, etc. And we also make simulations. That's what you just saw. We make simulation, we try to mimic the real Earth scenario, but the reality is totally different. We still have the capability not to predict earthquake. We cannot predict earthquake. All right. And not only that, these simulations are very, very expensive. How expensive? I'm going to tell you. These simulations are very, very computationally expensive. For example, the simulation you just saw, it took thousands of thousands processors to run that simulation, and it took days, not days, weeks to run that simulation. So it is computationally very, very expensive. And to make this simulation, we had to work collaboratively. Not only geophysicists, not only geologists, we have to have multidisciplinary collaboration. Geologists, programmers, software engineers, geophysicists, they have to come together and they have to write code and they have to fix the bug. So it's a tedious process, long-term process, but still we are trying to do this, right? So, and not only that, and for example, like even third world country or even the USA, most of the universities, they don't have that power. They don't have this access to the supercomputers, right? We have lots of supercomputers, but how many people do we have access to supercomputers? Very few, right? So we cannot run these simulations. That's why this is very expensive computationally simulation. All right, I'm gonna give you one single examples, like to get a sense how expensive this is. For example, this is a California, and there's still San Andreas Fault, and we have 3 different colors. Number 1, red one is like the already fault has been ruptured. So this region, for example, this is the San Andreas Fault, right? And in this region, couple of places, these places has already been ruptured, and you see in San Francisco region too. And the blue one is still active. There are a lot of microseismic tectonic things are going on there in these blue places. And the black one is still the locked. The Los Angeles area didn't feel that much earthquake very recently, that big. Why this is? That means this earthquake wasn't able to rupture this part because the material properties for this fault might be different from this property, or the earthquake happened here hasn't had enough strength to break this fault, right? But still we wanted to make the simulation. What are the parameters? What are the parameters are here? What are the material properties are here that will cause the earthquake? We wanted to know those parameters. If we can somehow know all of these material properties, all of these parameters, then we'll be able to tell this magnitude of earthquake will be able to break this fault, right? But still we do not know these material properties, still we do not know this sort of material parameters too. Then what do? Then we tweak this parameter and run simulation and do trial and error, and each simulation takes weeks, days, and we wait. And finally, whenever we see, oh, okay, this combination of parameters is responsible for the breaking the earthquake, then we see, oh, okay, these are the sweet parameter combination that will be responsible for breaking this fault. But how many months, how many years do we need to get this trial and error? Many, many months. That's why we still cannot predict earthquake, because we have the limited resources, limited capability, right? So this is where I thought, why don't we take the advantage of machine learning? Why we should depend on these expensive simulations? Okay, so this is where my thesis, my part of my dissertation comes in, and I use machine learning, and I successfully showed machine learning is able to predict the rupture of, not only able to predict the rupture of this fault, and it's also able to give you the combination of parameters. Okay, these are the combination of parameters responsible for this fault. All right. So before that, I'm going to teach you some of the failure about the failure theory, like how things break down. Because it's all about fault, because whenever an earthquake happens, this earthquake is break the whole fault, right? So it's a failure. That means whenever material fails, earthquake happens. So I'm just gonna give you a sense of failure. So how does it happen? So failure means, so for example, say this is one type of material, it could be a plastic, it could be anything, and the failure can happen in different ways. For example, one of those ways is tension. So if you pull from these two sides, right, and pull enough so that this tension is exceeded this material strength. Every material has its strength, right? For example, this material has different type of strength than this material has, because this is iron probably, or aluminum, and this is plastic. And if it were wood, then the material strength would be totally different, right? Would be smaller. So if you apply if you apply tension, or if you pull from this side, then eventually this material will break down some point. Okay? So this is one way. Similarly, you could apply compression. So you just push, and at some point, your force will exceed the material strength. At that time, the material will break. Right? Similarly, we have torsion, shear force, and among these forces, shear force is the very important one. So shear force is, so for example, we have x-axis and y-axis. You just push this direction. This is the x direction, and this is the y direction. So x-axis here, and if you push like in this direction, y direction, this would be like y component of the force. And if you push this direction, this would be the x component of the force. What is the shear stress? Shear stress has both x and y component. Both x and y component. So whenever your shear strength is pretty high, that means it's very, very likely that your material will going to break down. This is very dangerous. And that's what we see. I told you, remember, that a destructive wave is called shear wave. So this wave generally shakes us. Okay. All right, so this everything is kind of like translated into a very simple equation. And whatever I say, the failure mechanism, this failure mechanism could be explained by this very simple equation. So what this equation is, this is the material strength. So whatever the strength any material has, it could be rock, it could be mineral, it could be anything, material strength. And this is the applied stress. And this T, phi and C is the cohesion of a material, and phi is the frictional angle. This is called the material properties. So any combination of stress, material properties here, so if your stress is increases and material properties are kind of increases, then it's very likely that it's going to exceed this tau. Right? So whenever the combination of this parameter is going to exceed tau, at that point material will break down, material failure will happen. Right? So we wanted to see if we can learn the combination of this parameter. So still we do not know for the earthquake. The combination of what combination of parameter causes the earthquake? We do not know. We know theoretically, but the real life situation is very, very different. I'm going to show you. So our main goal is to learn this equation using the artificial intelligence or machine learning. See if we can do this. All right. So in order to interpret that equation, so what I did, so we started with the very simple rupture domain. So we have a 0 to 32 kilometer length and 0 to 24 kilometer width. So I'm just showing here very zoomed view so that you could see this heterogeneous fault here. And along this axis, you see here is the fault. And this fault has a very geometric bump, right? So we wanted to, and the earthquake happens here. So we wanted to predict whether this earthquake will be able to break through this fault. That's what we wanted to predict. Right? That's what I showed it to you in the simulation slide, because we still do not know what are the combination of parameters. Okay, so we wanted to learn those combination of parameters, and not only that, we wanted to learn whether this strength of earthquake will be able to break this fault. Okay, so this is the simulation setup. Like we still did simulation, and this we varied like these 8 parameters: height of the fault, width of the fault, and since you know the mechanics of how fault happens, we have the stress components along the x-axis and stress component y the y-axis, and the shear stress xy component. And we have the material properties: critical distance, stress drop, and dynamic friction. These are all kind of like physical parameters of this body here. So we simulated varying these 8 parameters. So we varied these 8 parameters, and different variation of 8 parameters, we got 2,000 simulation. So each simulation took 2 wall hours, 2 clock hours, and 8 processors. So for 2000 simulation, it took like 4,000 hours. It was like very insane. We used the University of Memphis High Performance Computing Center, and we had a very reserved, dedicated allocation for that. So we are very grateful to the University HPC Center. Anyway, so we used that. So now we wanted to see, and out of this 2000 simulation, I use 1000 simulation for training purpose, and just 600 for validation and 400 for test simulations. And you see this is still imbalance problem. 30% were able to break this fault. So whenever that 30% break this fault, we call it earthquake was able to propagate. So earthquake was able to rupture the fault. And if it didn't, then we call it earthquake stopped. Earthquake didn't break through the fault. Stop means like it even couldn't pass this bump. So we define this. So that means earthquake is somewhere, stopped somewhere right here. So earthquake didn't have, for that combination of parameter, earthquake didn't have enough strength to break this fault. Okay, so it's imbalance problem, and so that means we call, when earthquake is propagated, we call it positive class. When it didn't, we call it negative class. So it's a 1 and 0. It's a binary classification problem. All right, so here are a couple of examples. So here are the 5 examples, and you see our labels are either 0 or 1, and 0 is arrested, that means earthquake didn't propagate, and 1 is propagated, and their corresponding data. It's a very numerical data. So for the simulation, to get this 0 or 1, we had to wait 2 hours with 8 processors. So it was insane. Anyway, let's see, I'm going to show you one of the examples, like my simulation. The simulation users saw before, it was done by the Southern California Earthquake Center, but this is my simulation, like I have done by myself, using the HPC. So let's see. So earthquake started here. You see, the tip is propagating, right? And it's going to stop, and it wasn't able to propagate for that combination of parameters, right? And you see still the waves are propagating. So probably if we are here, then we'll be feeling shakes somewhere right here. All right, so this is the fault. And this is one of the examples of earthquake arrest. That means earthquake couldn't propagate. All right. So, as I said before, I used these 8 parameters, right, that I varied, and to make a simulation. All right, so these are the 8 parameters, and I did all sorts of pre-processing for the machine learning modeling. So I normalized this data. I developed this neural network, and this neural network is very shallow. We intentionally kept this neural network very shallow. It's not deep. It's a shallow neural network. Why? Because we wanted to explain the black box. Because most of the time we couldn't explain the neural network, right? Because it's a black box, and it's not only for neural network. It any kind of machine learning model, but there are lots of machine learning models we couldn't explain. It's a black box. Something is going on there. But we wanted to take one step further. We wanted to know what is going on there. We wanted to learn what neural network learns actually. Okay? And so we have 8 input parameters here. You see 8. And we have one hidden layer with 12 nodes. All right, and one output. So output would be either 0 or 1 because it's a binary classification. So we want, and in the first hidden layer, I applied ReLU activation function. It's a nonlinear activation function. And since it's a binary classification, I applied sigmoid. Right? And sigmoid is like this: X is coming from here, and W is the network parameter, and B is the bias term. So if you look at this activation term, sigma here, if W, X, and B all are positive, we're going to get a positive output. And if all are kind of like low or negative something, then we'll get kind of like around 0 output. Like the sigmoid activation function generally gives you score between 0 to 1. So if your value here, whatever the value is very large and is going to push us toward the 1, and all sorts of values, if these values are 0 or very close to 0 or negative, then it's going to push us to 0, something like that. So we wanted to see if W is positive or not. So these are the network parameters. So we wanted to learn these network parameters. All right. So and this is the ReLU activation function. So if you have any questions, just let me know. I could answer right away. Or I would try. Yeah. All right. So after I fed this data and pre-processing thing and did some data balancing issue and cross-validated and mitigated overfitting by regularization, L2 regularization, and early stopping and all sorts of things. So when I'm done with the training, I wanted to learn 8x12 matrix network parameters, right? That's what I wanted to learn. And also 12x1 network parameters. That's what I wanted to learn. I wanted to see what those 8x12 network parameters are, or what those 12x1 network parameters are. Why and how neural network learns specifically that parameters, and why is that? So I wanted to learn that. This is pretty interesting. And after training, I got some classification results. So rupture arrested propagation, and you see F1 score is pretty decent, 0.82. Though the positive class, the precision is a little lower, but overall, I'm good. I'm feeling very good that F1 score is 0.82, but still I do not care about the result. I don't care whatever the result is. I just care what neural network learns, and if the neural network is able to predict the right score. That's what I want. I don't care about this. Okay, let's see what I care. I care this. This is very interesting. And you see here, we have a 8x12 network parameters, and here is a 12x1. And if you look at this here, x-axis is your feature, 8 input features, and this 12 is a hidden units, right? That's what I showed it to you. And in the output layer, we have output unit and the 12 hidden units. All right, so what this is? So what does this mean? So what does this tell you? Okay, we wanted to explain. We looked at this figure days after days, and see if we could find out something. Finally, we found this network, nothing but this equation. How? Okay, so this, look at these examples, 12x1. Since 12x1, the parameter ranges from minus to positive, right? Negative values to positive values here. Negative, right? And negative values, I told you, if the network parameters is negative, then its tendency to contribute towards the negative class. If it is positive, its tendency to contribute to the positive class. But it may not be true, but globally it's true from that sigma equation, right? All right. So I'm going to give you one example how this translates to this equation. Okay, look at the unit 4. Just unit 4 at this 12x1 matrix. Unit 4 is purely purple and is the very, very negative, right? That means this unit 12 contributes towards the negative class, being a negative class. That means earthquake didn't propagate. Earthquake somehow arrested. But why? Okay, so if you come back to this matrix 8x12 and look at the corresponding 4, is a 4 here, and come back to the corresponding 4 here, then you would see height and width is a geometric parameter, right, of the fault, has fairly and strong positive weight. That means height, and in this particular examples, particular node, height and width contributes towards the positive class. But if you look at the shear stress, it's highly negative, and friction drop is very highly negative. So if you plug this into this equation, then you will see friction drop is negative. This combination of this parameter is negative, and the very strong component of your stress is negative here. That means if you look at this here 4, our normal stress is high, but shear stress is negative and friction drop is high, and friction drop is low here. In this case, earthquake was arrested. I'm going to give you one opposite example. Look at the 5. You need 5 here, 12 by 1. For this 5, and if you look back to the corresponding 5, you will see height and width has kind of like negative impact, right? And you'll see your stress is pretty high. Shear stress is very high in that case. And other parameters, for example, like normal, all the normal stress is low, and high shear stress is very high, and for this combination of parameter, earthquake was propagated. So if you pay attention very closely to this table, then you would see whenever we have high shear stress, we see this corresponding propagation. Most of the cases. That's what I told you. That's what this equation is about. So we are able to explain what is going on there. So it's not very quantitatively. It's not very quantitative. It's just high low. But how high is, or what the low is, right? We still do not know. There is some still uncertainty, right? We can solve this problem right away. It's not that hard because we have a Bayesian neural network. We have Bayesian statistics. We could apply these Bayesian statistics here and solve this uncertainty issue right away. How? This way. So this is so that is my first paper, and from here this is the second paper starts. So I'm still working on the second paper. The first paper has been submitted to the Journal of Geophysical Research. So from here I'm going to explain the second paper. Anyway, all right, so I use this same neural network architecture, but instead of defining neural network parameters 8 by 12 or 12 by 1, I define this neural network parameter as a distribution. So you know the distribution is just once you have distribution, mean and standard deviation, you could draw as many parameters as you can. So we are not limited to 8 by 12 matrix. We could draw infinite number of parameters. And we wanted to see, then we'll have infinite number of 8 by 12, 12 by 1, then we'll have infinite number of neural networks, right? So whenever we have infinite number of neural networks, if you feed one single example, then you will have infinite number output predictions, right? Lots of output prediction. So that's what it says. So whenever you have distribution here, whenever you have distribution here, for any given examples, you will have a distribution of prediction score. When you have distribution rather than a single point, so the last one, like vanilla neural network, would give you whether it's a 0 and 1, or some score, and this score would be either, for example, 0.69, 0.89, just one single value. But here, in this case, it's going to give you a distribution. So whenever you have distribution, you could calculate all sorts of analysis. For example, mean, standard deviation, entropy, and lots of statistical parameters, you say. All right? So see how it could solve the uncertainty. All right, so we trained that network same way. We had the same training data, validation data, and the testing data. So whatever you see here is based off of test data analysis. All right. So this is the very interesting plot. I like this plot a lot because this is one of my favorite. Why is this favorite? And I'm pretty sure this plot will be favorite to your case too, because this translates the real life scenario. I'm going to give you example. This example would be real life examples, and you could apply these examples in your applications. How? For example, say I had a 400 test simulation data points, right? And if you look at this here, my BNN, Bayesian neural network, give me predictions. So these are the frequency here, and y-axis is the probability, prediction probabilities on this plot here. So you look at this here. So you want for any given input data, whether it be 1 or 0. So for 1 cases, all the prediction should be around 1. Prediction score, right? And for the negative class should be around 0, right? That's the situation. But yeah, we see that most of the prediction scores are around 0. That's fine. And most of the prediction scores are around 1. That's good too. But still we have a couple of data points that has prediction score from 0.35 to 0.75 or in between that, right? Why is that? Why this is happening? Because these are the examples that have both earthquake rupture at the same time earthquake arrest behavior. So this type of examples has two types of behavior common. So this is where our traditional neural network fails. Whereas the Bayesian neural network now tell, okay, so these are the examples are having both types of characteristics, right? So now, whenever we separate this out and you see here in the corresponding uncertainty, how uncertain those examples are. You see uncertainty kind of increases from 0 and all the way up to 0.5. That means examples with prediction scores around 0.5 have a very, very high uncertainty. And if you again come back, this region has a very low uncertainty. But the question is why? As I told you, those examples has both earthquake, like positive and negative, both behavior. And not only that, these examples are very unknown because I didn't use the test data for training the model. So this test data is totally different, right? So there might have the case that there might have some of the examples that are totally new in test data that my training data has never seen. So what does this indicate? This indicates that if this neural network is able to predict future trend, so for example, you wanted to build a new classification model today, you have a bunch of training data, right? And you come back 3 months later. 3 months later, you have a new test data, right? And you have new test data, and it has different type of pattern that your neural network or your classifier haven't seen before. But this model, like Bayesian classification, Bayesian neural network, is able to predict this new pattern too. Then Bayesian neural network would be tell, oh, okay, I have never seen this type of data in my training data. That's why I give very high uncertainty score. Right? So that's the beauty of this. All right. And these are the corresponding 2D visualization. So I'm not going to go over that. So now you learned, okay, so there are a couple of examples that has a very, very uncertain, and there are a couple of examples not very uncertain. All right. But I wanted to find out where this uncertainty coming from. Why? Say you gave this example and you see prediction score and uncertainty, and your uncertainty is very high. You wanted to find out, you wanted to pinpoint the very specific source, like what are the source for this uncertainty. If you could find out this very specific source, then you would be able to solve that specific problem, not the all over the global problem, right? So I wanted to find out that kind of thing too. Okay, so what I did, I use permutation importance techniques. I applied this technique to Bayesian neural network case. So what this technique is? So probably many of you guys are familiar with. I train the neural network with the training data as simple, and I measured F1 score. The F1 score, remember I told you, 0.82 is a base level score. So what I did, so we have 8 features, and one by one I shuffled one feature. For example, I keep all 7 features same, variable same, and I shuffled this feature, shuffling. So that means this feature is kind of like noisy, corrupted. And I wanted to make prediction with this noisy feature. So that means I shuffle 8 times for 8 features, and every time I get a prediction and uncertainty, right? And I measure, for each feature, I measure how much prediction error kind of deviates from the base level. So this is how I kind of like compute, I can compute the feature importance from that. So that's a very normal thing. All the people do this all the time. That's fine. But then what is the advantage? I wanted to make the profile of uncertainty for different classes. For example, if my earthquake rupture class, earthquake arrest class, I wanted to make the profile of uncertainty. What are the features for earthquake rupture is providing uncertainty, this kind of things. So for the 8 feature, and I have like 400 test data, so I will have 8 by 400 predictions, right? Plus uncertainty, since it's a Bayesian neural network. And so whenever I have the prediction score, then I find the optimal threshold that maximizes the F1 score. Based off of this threshold, I am now able to classify whether it's a rupture or not rupture. Then I will have true positive class and true negative class based off of that threshold. Okay. Now you see, whenever earthquake happens, certainty or uncertainty comes from this order for this true positive class. So you see here, for the true positive class, uncertainty is a little higher than the true negative class, right? And the uncertainty is mainly coming from stress. Similarly here, mainly from stress, but the order is a little different. So now, we can solve the uncertainty problem too. So remember, from the vanilla neural network, we are able to get the different combination of patterns. And from the Bayesian neural network, we could solve the uncertainty problem. Not only that, we are also able to tell whether this earthquake is able to break through this fault or not. All right, so these are the kind of like some main summary of this whole study. So I'm almost done. So I showed it to you that so we could get the patterns responsible for earthquake rupture, and not only that, we can make uncertainty profiles for earthquake rupture. I don't even care. That's fine. Do you know how I reduced time from 2 hours with 8 processors to fraction of second? With a fraction of second, now I'm able to tell you this earthquake is going to rupture fault. And because with the same combination of parameters, remember I had to make a simulation to know whether this earthquake is able to break through this fault. Now I don't run a simulation. I just give the same parameter to a neural network to tell me whether this combination of parameters is able to break through a fault or not. Now neural network can predict fraction of second. And this is why Los Alamos National Laboratory, they were very interested. They invited me there. I gave them a talk. And probably they're going to implement this to a probabilistic seismic hazard model. And I got a feedback from Harvard University that they're also interested to implement this method because it's a super fast. They don't have to wait like months, weeks, right? Within a fraction of a second, any parameter of combination, you'd be able to tell whether this earthquake is going to, though it's a simulation, it's not a real life, but still it's a one step further, right? I was able to reduce the time. All right, so, and the BNN can even identify the feature uncertainties. So, at Asurion, we leverage this research. At Asurion, we do cutting edge research. We have lots of data scientists, we have machine learning engineers, so we combinedly do our research there. It's a totally R&D. We do lots of research, we have lots of freedom, and we take the advantage of our previous research. So for example, we use BNN. We do not use BNN right now. We are planning to use BNN, and we are conducting a research how BNN could able to solve our different Asurion problems. For example, like fraud, future patterns, customer and tech support issues, and many, many more cases. And predictions explanations are very valuable, and we wanted to know why, because it's a real life situation. Any kind of decision we make is going to impact our customer, right? But we wanted to make a very good decision. So in order to make a very good decision, you have to have some information, and this information could come from BNN or vanilla neural network, as I showed it to before. So we leverage this type of research. So not only me, all the data scientists, all the machine learning engineers do this type of work at Asurion. And of course, so we are expanding our research using shallow neural network and other algorithms, and we use multiple GPUs, multiple CPUs to handle massive amounts of data. All right, so this is the end of my talk. I hope it was not that boring. I hope, if you have any type of question, just let me know. And by the way, oh, I forgot. So all the codes, so these are my research thesis topic. So all the codes and even the paper are available in this link. So if you want, you could take this, use these links and code. All the codes are available for the BNN here, and the vanilla neural network here, and the paper here. But the second paper is still on the way. So I hope I will be able to put this later. Thank you. Yes, sir.
So you mentioned in looking at feature uncertainty that you shuffle the values of each feature one at a time. What's the rationale of doing that rather than injecting a certain amount of noise around the current values that you have a little more control over? Because you could shuffle two things that would never, such that the swap is a very improbable point.
Yes, that's a great question. Yes, you could do either way. But this is faster, and this is one of the established methods that lots of Kagglers do, like to get the feature importance. But you could do the other way around too. That's fine. Yes.
So with the neural network, you mentioned that you save a lot of time with that. You still have to do. Is that like initial investment of the 600, simulations and
yes.
Or to do your training testing? You still have to do that upfront investment, but once you've done that, now you can do 1,001 simulation and it doesn't take you 2 hours.
Exactly. Yes. So because see, I told you we don't have data, right? So we have to get the data through simulations. Once we get this data through simulation, then rest of this kind of like very fast. Like 400 test data point takes like fraction of a second, not one example. It's like one example would be like milliseconds, something. Yeah.
So when you were studying like the weights in the shallow neural network, when you tried like adding a higher number of like neurons in the imaging layer, I was just out of curiosity, like how did that graph like change?
Oh, how did they find this architecture?
Yeah, and like how did the weights change? Like how did the performance of the weights change when you added more neurons in the hidden layers?
Hold on a second.
Y12.
So, if I understand correctly, so your question is how did the weight change?
Yeah, and like Y12 neurons in the hidden layers.
Yeah. So 12. This is the one hidden layer and 12 neurons. Yes.
And so how did the performance change when you had more neurons?
Oh, okay. So this is the optimal neural net because our objective was clear. We wanted to have shallow neural networks. So we tried with different kind of architecture, and we found that with this shallow neural network and one hidden layer and 12 nodes, the most performance is gotten by this kind of things. So it's kind of like trial and error, like grid search or something like that. So, yeah. Yes.
Just for some context, what was the simulation, or what were you doing in the simulation? Was it finite element?
Yes. So it's a curve. It's a finite, and not the finite element. My other, the first two part of my dissertation was based on finite element, but this one is curvilinear finite difference. Yeah, finite difference, but fourth order Range Kutta model. Yeah.
Okay. And as a follow-up question on the feature uncertainty, using that method, doesn't it really want to look at first order uncertainties, or uncertainties to first order effects? Did you ever swap multiple features at the same time?
Swap like from one feature to another. No,
It's not necessarily that two features at the same time.
or two features the same. No, I didn't try it out. No, I just tried only one feature, and I just wanted to measure like what is the uncertainty for the corresponding feature. Yeah. Yeah, that's a good idea. Like we could do, say for example, like two features shuffle together and see what is the combined uncertainty for this, right? Yeah, yeah. So yeah, that's an interesting idea. Yes.
I'm just curious whether you saw the Cabo competition that was Los Alamos National Laboratory earthquake prediction.
Yes.
There was like a single feature.
So you have a seismogram, and from this seismogram you have to predict what is the likelihood that next point or next couple of points is gonna break. Yes.
Right.
I'm familiar. Yeah.
So it became like the feature engineering.
It's a total feature engineering because you are just only given one bunches of wiggles. That's it, nothing else, and you have to come up with like lots of features. So I saw people use CNN, people use like vanilla feature engineering kind of things to get features out of that. That was very fantastic. I was personally not involved with this project. My professor was involved with that project. Yeah. Yeah.
One last question, sorry.
No problem.
In the simulations that you put together, I'm sure there's a ton of work behind it. What kind of effect, was it a homogeneous layer? Or do you have as far as the material properties?
Yes, I intentionally skipped the physics part because if I added the physics part, then it'd be like very long talk. Yeah. So the material was varied. So if I go back to the, you see here, this is a two-dimensional case. It's a two block, like right above the fault and right beneath the fault, and this. So we apply forces this direction for the upper block, and we apply these forces in this direction. So that means two blocks slide past each other, right? So in this case, material properties are homogeneous. At this case, we wanted to do the heterogeneous material properties too, but that is another story because it took us a long time. So we kind of stop there and kind of like work on that homogeneous property right now.
What's the gold standard for building the simulations in the first place? Can we take real data from seismic activity and make sure that the simulations reproduce what you measure, or are there too many missing variables?
Personally, I don't find any gold standard. Yeah, of course there are gold standard. We wanted to validate this wave, right? That's what people have been doing in Southern California earthquake region. So for example, say, even at this, so what you could do, you could validate your, so remember for this earthquake, right? So these waves are propagating. So you get some shake, right, whenever you get the shear wave. So what you could do, so we have like lots of historical seismometer in some places, and this seismometer captures this wave, right? So for example, say you had, like long before, you had 7.8 magnitude earthquake somewhere else, and you captured this data. For that part, say, for example, say you have a seismometer here, and you have this historical waveform. Now you have this simulation, right? And you will get the same type of, not the same, but almost the same or something. This way you could validate your like historical data with your simulation data. That's what.
Can you impute the forces, the shear forces from seismic activity kind of back, calculate how much force did it have to be?
That's what people, yes. So at our university, we had a simulation group. They were able to do this, but I'm not familiar with this because I didn't work in that region. So I'm not that super familiar. Yeah, but people have been trying to do that.
Go back to the slide where you show the three maps of the parameters and the biases.
Yeah. This one?
Can you explain how you get the last column in the table at the bottom, the prediction?
Last column? Like this one?
Prediction, yes.
This one?
Yes.
Oh, okay. So this is how we determine, because so from this equation, if you see, if your stress is very high and your material properties are very high, right? Then if you exceed this tau, then your failure will happen at the time. So failure means like earthquake is able to propagate, right? And non-failure means arrest. So if you come back here, oh, we have a high shear stress and high friction drop. you kind of like elevated shear stress pretty high and friction drop is pretty high here, somewhere right here, then tentatively you could say probably there will be a failure. So we call it propagation. I hope, is that answer? Okay. Or any other question?
So besides using the Challenger network, did you use any other methods?
Yes, I did. I kind of skipped. My first paper, this paper is random forest too. So I used the random forest just to see this algorithm and the neural network algorithm results are kind of like overlapped, and interestingly, they are very similar. Yeah. So if you go back to my paper, if you read the paper, then you'll see like I kind of like listed down everything there. Yeah. And one of the good thing of random forest is that you could get the feature importance, right? So important features. So I kind of like try to compare the feature importance from random forest and my version of explanation, and they're exactly the same. Not exactly, like they're almost the same. Yeah.
Do you think explaining it this way would be feasible for like a multi-layer neural network?
Oh my gosh, no. No. Like I couldn't even think of like I could go beyond 2 or 3 layers. No, it's not. That's why we intentionally kept like 2 layers, 1 layer. But people have been trying to do, for example, like CNN, people have been doing like all sorts of like what the intermediate neural network have been learned, something like this. Yeah, but for this deep learning these kind of things, I didn't try, and I personally believe it'd be complicated. All right then, thank you very much.